PhD Research Fellow in the Research Fellow Scheme by HKRGC in 2022. She is also an associate editor in Process Safety and Environmental Protection and editorial board member in desalination. She has also been conferred the City University Outstanding Research Award for 2023 in the junior faculty category in recognition for her outstanding research, development, and knowledge transfer achievements. So you seem to have a lot of feathers in your cap, Professor Alicia. That's so nice to note.
Thank you very much. Yeah.
So we have our main timekeeper as Professor Deka, and he has given me time that it starts from now, and you are expected to go till about 12:10. So maybe I request you to finish about 5 minutes early so that we can have some questions on your presentation. Right? So I give the mic to you. Thank you very much.
Okay. So good morning there. So thank you, Professor Deka, for your kind invitation, and also the colleague in IIT UK. So it's been a really pleasure to give a talk in this occasion. As you know, the Professor Deka got a PhD degree from City University of Hong Kong. And our earlier, the keynote speaker, Professor Song, is kind of my mentor. And also I see also some the researcher who graduated from City University of Hong Kong. And also one of the speakers is also my colleague from the University of Tokyo. So today my talk is something I'd like to share, the advancement in nano-enabled membrane distillation for sustainable water energy environmental nexus. So Professor Song has shared his expertise on resource recovery from the water. So my talk is we are having the same directions, but different approach that we want to expand our desalination technology not only for water, but also energy and environmental nexus. So today my talk has three dimensions. So the first, I will start with my talk in fundamental advancement in the nano-enabled membrane distillation. Let me use that pointer. Okay, yeah. And then my second part will be water energy environmental nexus with industry attachment. So the first part will be more likely the fundamental understanding of this the technologies. And the second part of my talk will be how we can scale up with the industry connection. And then last part will be knowledge transfer. So I would like to start by introduction of our water cycle in Hong Kong. Hong Kong has a very, very unique water cycle. This means our water is like Singapore. Most of our water is imported from the outside of Hong Kong. So we've been working on how to improve these water securities, and by just promoting this passive, like improve the usage and also the increased supply was not very practical enough. So recently what we do is we want to increase the reuse of wastewater, which means wastewater reclamations, and we will start desalination. So our first desalination plant will start to operate next year. So this is our water the cycle that we have a very diverse water resource. So starting from the local yield, which is only at 20%, and we are pretty much depends on the water from China, which is from the Dongjiang River. And also, this is very interesting that we used to use and is still been using the seawater for toilet flushing. So by having seawater direct pump and the simple physical the pre-treatment, it can save about 20 to 30% of fresh water, which will be used for the toilet flushing. So this was the current water pie chart. And now we are going to have a desalination plant and recycled water. So also, I also learned a lot from the Professor Song's talk that when we have a desalination, the brand will be also issues. We also need to think about how we can either capture the resource from the brine or increase the water production, etc. All right, so let's look at our water cycle. I think we all learned this water cycle from like primary or middle school, which illustrate the water will be evaporated by sunlight, okay? And so these evaporations and the precipitation through through our nature clouds and also the rainfall. So the water from this precipitation is actually 10% of our freshwater resource. It's coming from the water captured in the atmosphere. So you know this water phase, the capture in the atmosphere is vapor. So when you look at this process, the water is always changing the phase, liquid phase, vapor, and liquid again. So we learn from this natural water cycle that our group has been started to think about, can we actually engineer this water cycle system? So in order to do that, we need to understand this energy balance. So when you look at this water vapor, so water vapor is very important energy carrier. So it can be used for the power generation and the sterilization or water purification. However, this water vaporization, which thermally changes the water phase from the liquid to the vapor, require very intensive energy. Why? Because we need to break this hydrogen bonding. At the 30 degrees Celsius, in order to evaporate 1 kilogram of water, we need to have 2,500 kilojoule. So learning from this our nature, we try to engineer this water cycle into membrane base of distillation process. So unlike we have to distill at the 100 degree, if we can create a temperature gradient across this hydrophobic membrane from the speed water and the permeate water, by having this pressure gradient, which can be the driving force of water evaporation and condensation, actually we can evaporate water at even 60 degree or even lower temperature. So that gives us an opportunity that we can use the renewable energy, we can use a low-grade heat. So to overcome this high enthalpy of water evaporation from this distillation process, changing the water phase from the liquid to the vapor, I think it gives us a lot of opportunity that we can engineer the system with low energy input. So the membrane distillation concept is very straightforward. This is similar to distillation process. However, we use the membrane, which is hydrophobic, to prevent water cross the membrane. We only allow the vapor to cross the membrane. So this cross the vapor, again, condensate, which will give a very, very high quality water production, and which allow almost 100% of salt rejection, as long as there is no wetting and fouling. So it can be used for wastewater reclamations, and also it can also combine with the RO for brine treatment, etc. And not to mention the opportunity of the low-grade waste heat were coupled with the solar energy, which I will spend half of my talk with this integration of solar energies. Okay, so recently we were very lucky to publish advanced material, the paper into the advanced material to review the membrane distillation with focus on the nanomaterials. So if you have a chance to read our recent publication, you will understand how this membrane distillation has been, in terms of the timeline, has been actually developed. And if you look at this, our number of paper actually exponentially grows from the 2000. That is actually starting point that after we start to have a membrane, which is Gore-Tex PTFE membrane, before even we understand this concept, because we didn't have a proper material, We didn't have a proper those modulation system. So that was only remain as idea, and then there was not much publication. But after we start to identify, okay, so we can produce the membrane, the materials, and also we can modify the system. And from the 2000, the paper publication has been increased exponentially. And also recently, you can find a number of industry also join into the membrane distillation community to make from lab scale to closer to the commercialization. Okay, so when we studied this membrane distillation process, we actually found 3 domains of in-stream limitation. The first is membrane degradation. That is the same to any other membrane process. So not only this membrane distillation, most of this pressure driving process will suffer from fouling, scaling. But in particular, a membrane distillation process, because this has to be hydrophobic, and we have to remain this hydrophobicity to block this water liquid passing through. So wetting is another in-stream limitation. Okay, so the temperature polarization. This is very important in order to understand this fundamental behavior of the membrane distillation process. Because we have to increase the water temperature in the feed site, even though we can utilize this pressure gradient so that we can evaporate water at the lower temperature, but still water temperature has to be increased. The problem here is when we increase temperature in the feed site, right? And the driving force is actually the temperature through this membrane. So there is always a gap between the temperature in the feed side and the temperature at the membrane is because of the energy loss. And that created this temperature polarization. So you can see delta T from this one to this one is larger than delta T from here to here, right? And also because of that higher temperature here compared to this, the permeate side is also due to the latent heat. And this all bring high energy demand. And also, again, this is thermal-based process. So we need to provide a very high enthalpy to break hydrogen bonding as well as change this liquid phase to the vapor phase compared to the other pressure driving process. And also, not to mention about this biological process of wastewater, which you can see this big gap of the energy input in terms of kilowatt hour, right? Okay, so in terms of the enhancement of a membrane distillation process, so like here, Decca and also Dr. Guo, who will give a talk after my talk, has been working very hard. And also we have published quite a number of papers to enhancement of the membrane performance. We changed the membrane structure and also surface chemistry. And in terms of the energy part, we are still working on whether we can directly use the solar energy instead of the energy to increase the feed water, which will increase the bulk water temperature. So our study first, we focus on this membrane performance, and then we recently tried to integrate with the direct solar drying process. And then, based on our knowledge, we learned this sunlight, this photothermal energy can give us more opportunity that not only for the water production, by manipulating or smartly utilize this nanomaterial, you can generate the cooling water at the same time, generated energy such as hydrogen, or you can reduce the carbon dioxide. So this is our ongoing work. And we have quite a number of publications in the membrane performance. And also recently, we also published in Nature Communications for solar drive membrane distillations. And this synergetic application is on the pipeline, starting from Chemical Engineering Journal. We are expecting to have a very high quality publication in the coming years. So this is our role in advancing the membrane distillation membrane and the process starting from 2015 to our recent time. And also you can see the name of Dr. Guo and also the Dr. Decker here. And also it generated not only the papers, it brings a lot of fundamental research and also integration with industry, as well as also the others internal funding. Okay? So, and here some figures are like main feature how we improve membrane surface chemistry to have a very high superhydrophobic, which can even repel the water and also keep very low surface energy to let the water to bounce on the surface of water. And you can see here that our the membrane has even omniphobic, which can also repel the oil as well. And this is the illustration that how we can concurrently produce water at the same time, hydrogen, also reduce the CO2. So let's start one by one. I don't want to spend a lot of time on the membrane because we actually have quite a number of attempts to improve the membrane chemistry and the structures. So this is kind of image. And just want to show this one of the video showing that you can see with our membrane, we have made a very high repellent to waters. And you can see that once water is contact with the membrane, it just easily roll off. So this is very superhydrophobic and also the omniphobic membrane. Something I want to share, a very interesting story that actually we plan to submit in the very high impact journal, that we also learn from the nature that, we understand the kind of spring-tail surface chemistry, and we discussed with our former PhD student who now become a faculty at the Xi'an University, Dr. Guo, that can we actually pattern this spring-tail into the membrane chemistry? So we've been working on this quite a number of years, and recently we made a very good result that based on this PS, the polymer structures, we actually make mimic these spring-tail structures. So, and also that you can see from the video that this is very, very high, super hydrophobic, and when water is contact with the membrane surface, it just have a very jumping effect, which demonstrates the membrane has a very, very low surface energy. So why low surface energy is good? Because it has a very low ability to capture the water, so only vapor will cross, and all this foulant and scaling will have a very, very minimal effect on the membrane surface. So which means membrane can be very strong, anti-fouling, and also the anti-scaling, and not to mention about the wetting part. So not only we make a membrane, we also developed a tool to monitor, because it's very difficult to see what is happening on the surface of the membrane chemistry. So all of our team has been working on this optical coherence tomography to understand this is kind of 3D image that what is happening on the surface of membrane in real time. So using these optical tools, actually you can see the dynamic between the membrane and this foulant, and also any type of the materials which actually passing through this membrane. So we were one of a very active group where we published the number of papers using the OCT to understand the dynamic between the membrane and the foulant. And in terms of wetting, at the initial stage, we only depends on this flux and the permeate quality. But then we realized that there is always a delay of wetting, that once it happens, it's too late to revert. So I work with also one of my students. Can we come up with a good idea? So actually DECA has contributed a lot on this non-invasive, the real-time monitor of the wetting progression in membrane distillation using impedance. This is electrochemistry that you use the current to see the impedance. So they will give a different pattern when there is wetting and no wetting. So we can have an instant signal of the wetting rather than wait that wetting happen, and then you will have the effect of the quality of your permeate. So we have also published quite a number of papers. So this is something very interesting I want to share that recently we just found a nanobubble study is very interesting. We have some project on the nanobubble with the aquatic chemistry and also the working with the fish farm. Along with it, we found that this nanobubble can be very good kind of cleaning or pre-treatment for the membrane. And first, we try to understand this nanobubble characteristic. So we have published a review paper just recently accepted, and the review paper on nanobubble, where the title is "Small Bubble Make a Big Differences in the Water Chemistry." So we review how nanobubble is being used in the different field of water and wastewater treatment plant. Okay, and we have done some characteristics. So you can see that as nanobubble mentioned, the size of the bubble is like 100 to 150 nanometer size. So how can we see? You cannot see with your bare eyes. So we need to have a laser point so that you can see with nanobubble, you can see the light is reflected. So you will see this laser beam color. But without the nanobubble, you don't see any color, right? And so what is different between nanobubble and the microbubble? They are so stable. So microbubble, after a few minutes, it just burst and disappear. But nanobubble stay 14 days, even a month's time. So we apply the nanobubble into the membrane, and we try to delay wetting and the fouling and scaling. So nanobubble on the membrane distillation on the delay of scaling, it worked very well. So we published one research paper and the chemical engineering journal papers. And so something we found interesting is that when you actually assist this nanobubble, the membrane can have can keep hydrophobicity or better than without the nanobubble. So this is kind of indirect result that the membrane can keep their hydrophobicity in the long term. Okay, so we are still investigating, and hopefully we will have a more good publication in coming years. Okay, so now I'd like to introduce the thermal efficiency enhancement in the membrane distillation. So as I explained, the water cycle, right? So in order to have this water cycle from liquid phase to vaporize and the condensation to create the fresh water, we need to have a lot of energy, right? But now you're looking at this solar, our nature system, we use solar energy. And do you think all this solar energy can be absorbed 100% by water? No. The only 20% of the solar energy can be absorbed by water, and also that is used for the heating the bulk water. Okay, so because it is not directly used for changing the phase of the water. So in the study early stage, because we use nano-enabled material to directly increase this bulk water temperature. But as I mentioned, right, because there is a lot of energy loss. You can see here that the evaporization, right, after losing a lot of energy, the energy change the phase from the liquid to the vapor is only minimum. But of course, depends on the material. You can increase this solar evaporation rate compared to direct this bulk water, right? So what is a smart way we can increase the solar absorption rate? We can make a different layer, so which means you can localize heat. So you can make one layer which can be the localized heating system so that all the energy will be captured here, And the water phase change is happening in this layer instead of this bulk layer. So there have been many studies published for this solar evaporations and using the many different materials. Okay. Then we found that there is a thermodynamic limit, which means, as I mentioned, 1 kg of water, well, we need the enthalpy of 2,400 kilojoule. Okay, and also to change the water phase, right, there is the required energies, and also because under the one sun, 1 kilowatt, right, we have a limitation of this the efficiency. So how much we can produce water with at the thermodynamic level? That is 1.5 kg per square meter of square meter of base materials. So how can we go beyond the thermodynamic? Because you know this watt flux 1.4 to 1.5. Well, if you have a large surface area, if you have abundant land, it's easy. But like Hong Kong or like urban city, where often have the space limitation, maybe it's not very practical. So we can further improve by change the structure of this evaporation layer to have this insulation at the water pumping. And the recent paper, including our paper published in the Nature Communication, we have received up to 3 kg per square meter. That is combination of the localized heat as well as kind of modularization of your reduce the energy loss by having the insulation, which means you try to maximize your driving force. Okay, so then what we have done, so instead of this standardized membrane distillation, which has temperature polarization, we try to localize the heat on the surface of the membrane. So you can see the temperature on the membrane surface is higher, right, than your water bulk. Here, your membrane temperature at the membrane is lower than your bulk, but here is higher. So you can maximize the delta T, which means you can increase your driving force. So at the beginning, we used a very common material to just test it, because the literature has already shown and summarized what kind of material can have a better solar driven interfacial evaporation efficiency. And this is the equation of specific water production. And its material is metal. And the material which has a high the solar absorption rate is good for this solar driven interface evaporations. Of course, this plasmonium and platinum is good, but this is expensive, right? So something black and also which has a sufficient and efficient solar absorption will be good. So we have done some study and we identified the number of materials. And we have tried this titanium. We have tried the maximum base of materials. And the reason we use the maximum base material is it has a very the broad solar spectrum and also the very high solar absorption rate. So in our the last paper, so we have a number of papers published in the based on this two dimension of the maximum material, where combined to this membrane distillation, which demonstrate very outstanding photothermal and also localized surface plasmonium resonance. So one of our key point here is, as I mentioned, the water flux over solar efficiency. We have achieved more than 90% with about 3 kg, which is beyond of what those thermodynamic level, and one of the top performance in terms of published literature. So we have shared our knowledge into Nature Communication. Now moving into synergetic application. So this is something in ongoing work, and we are in terms of the experiment. Okay, we are having some good results, And in terms of material, we have reviewed and published in the advanced material. So the wonderful study is we learned, okay, so by manipulating this catalyst, which is the photothermal and also catalyst, and Maxine was known as a very good co-catalyst, which means Maxine can be work as a photothermal agent. At the same time, it has a very good compatibility to work with other catalysts to give us another functionalities. So we have tried this Maxine and the TiO2 as an user study, and recently we're moving on to the CDS to concurrently produce the hydrogen. Okay, and this is all the characterizations. Okay, yes. So first, we have demonstrate this catalytic effect by showing dye degradation, and as you can see here, after some time later, the dye from blue color was completely removed and become crystal clear under photothermal reaction. So basically, you don't need to input any electricity, solar energy free. By utilizing material to improve your membrane performance, you can produce clean water at the same time remove this pollutant. Okay, so this was the already published work, and we have also summarized this mechanism in our paper. And now this is unpublished work for the hydrogen solution part. So initially we tried the same material, but it has a limitation. The reason is because as you know, to generate the hydrogen, this is a water splitting process, which means you need to have hydrophilic layer because water molecule has to you need to split the water molecule. So what we did is we strategically we developed the hydrogen layer with the Maxine. So which means we will have this hydrophilic layer where you can uptake water, all right? And then at the same time, the light to heat conversion is taking place, and also the electron carrier to convert your energy from the light to heat, okay? And then from there, so that is a kind of synergistic effect of water splitting. At the same time, the hydrogen conversion is happening in this system, okay? So we were somehow very struggling in the fundamental scale that because we need to somehow optimize where is the best condition not to lose this hydrophilicity, which means the water splitting. At the same time, to keep this capacity of the light to heat conversion based on this material. So we did a lot of study to understand this photothermal catalytic HER mechanism. All right, and this is the image of the recent the membrane. We are still optimizing. You will see kind of this porous hydrogel layer, and you can see kind of very shiny color. This is hydrogel, and also the color is dark because of the Maxine. And we were successfully regulated this hydrogel layer thickness because many studies published they have very, very thick hydrogel layer. Well, there is always a trade-off between the thickness and your permeability, right? So we were successfully control these hydrogel layers so that our recent results show that we keep this localized surface heating at the same time. We have good hydrogen production, which we reached to about 3,000 micromole per square meter, which is very comparatively high compared to our existing literature. So the other study for the CO2 reduction part is we are making some good progress. That one of my students also working on this to make this Maxine TiO2 material to membrane here. And then, so our recent study show very good result on the hydrogen CO2 conversion to CO and then methane. And this is our system that initially we have a very small scale system, and recently we designed. This is a photocatalytic CO2 reduction and hydrogen reactor. The inside, this is solar simulator, and this is a reactor, and directly connect to the GC. So before we had a difficulty of kind of the accuracy, but now whatever we generate in the hydrogen or reduction of CO2 and the CO and the methane generation, the data will be directly sent to GC, and we automatically monitor all the reaction happening in the system. Okay, so I think I will, because of time limit, I will just present this is last slide. So we start with this fundamental research to understand the mechanisms and also the process scalability of the membrane distillations. And we also work with the industry for this is seawater zero liquid discharge, the resource recovery using the crystallizer or pilot scale. And also we applied our membrane distillation for textile wastewater where the company actually produces gin. So our produced water can be used for the laundry. So we try to achieve the zero liquid discharge. And this is color from textile wastewater, and this is recovered water. And recently we are transferred this our knowledge to the in terms of startup companies and also the patents, etc. Okay. So for the this is some project. But in terms of our transfer knowledge, okay, we have a company. So now we are working on some developing the novel membrane, and this is the image of our students' competition, etc. And the last but not least, I'd like to acknowledge the all this support from our research grant council and innovation and technology commissions in the EPD, and also our university and also the industry, the APRO, advanced technologies. And yeah, so thank you very much for your attention.
Thank you, Professor Alicia. Thank you very much for a wonderful presentation. And as we can all see that you have a number of accomplishments and you have really achieved the technology transfer of many of the technologies developed. So really congratulations from all of us here on your success and future endeavors so that which can bring you more, more and more success. So I fear we may not have time right now for the questions, but I'll request all the members of the audience, if they have any questions, you may kindly write it them and send it to Professor Deka, and who will be able to pass it through to Professor Alicia so that they can get.
Absolutely, yeah. So this time, I'm very sorry that I really tried to visit in person, but I couldn't make it. But definitely, I will visit, in the coming years. And also, maybe I will find the opportunity to invite the DECA and some of your colleagues to visit Sydney University, Hong Kong.
Great. So there is a standing invitation for you for all the times. You can visit us whenever you like. So we are waiting for you all the times. And please put your hands together for a wonderful presentation. Thank you once again.